Our next speaker at the Haskell'23 Symposium is Abhiroop Sarkar from Chalmers University of Technology, and he's presenting the paper HasTEE, Programming Trusted Execution Environments with Haskell. Please go ahead.
Okay. Thank you, everyone, for coming to this talk on programming trusted execution environments with Haskell, specifically a domain-specific language called HasTEE. I must begin by saying I'm very glad to speak in a room full of Haskell programmers because I've done it the other way around, like presented this to hardware researchers and hardware designers. And I had to answer questions like, what is a monad? And what is Haskell? So let's start with the authors. So I'm Abhiroop, Abhi, on the top left. My co-authors, Robert and Alejandro, are present in the crowd. And Koen could not come to Seattle, but all of them have been very instrumental in the development of this project. So let's begin with a typical cloud deployment scenario. We have a set of applications which shares some kind of virtualized hardware, and there is this invisible layer of software that lies underneath the operating system, the hypervisor, and we tend to call this the trusted computing base. We trust it that it will do the right things, and you will see the dotted line goes past the applications as well. So what I'm indicating is that there are things like the language runtime as well, on which we rely to do wonderful things like memory allocation and threading and scheduling. Now, security researchers will tell you it's not a good idea to trust this software because there are various well-known vulnerabilities where you can attack the operating system, the hypervisor, and compromise the software that lies underneath. So what ends up happening is even if you use a strongly typed, theorem-proven software at the top level, bugs and vulnerabilities in the lower level of the stack will result in the fact that all of the applications at the top will end up getting compromised. And hardware vendors have been thinking about this for some time, at least 10 years. And the solution that they come up with is called Trusted Execution Environment. The general idea is that you have a disjoint portion of memory, and any kind of confidential code and data that you have would reside on the Trusted Execution Environment. And even if there are bugs and vulnerabilities in the operating system, that will not affect the confidential code and data that resides in the TEE. So a natural question now is, how do you program TEs? So before that, I just want to say that pretty much all the well-known hardware vendors like Intel, ARM, RISC-V, all of them have been thinking about this, and they have different ways of implementing this. So for example, this disjoint piece of memory could be the virtual memory, like Intel, or it could be the physical memory, like in ARM or RISC-V. So coming to the programming of TEs, the general approach looks like this. First of all, you program in a low-level language, preferably C or C++, and you divide your application into two projects, a trusted project and an untrusted project. The trusted project is much smaller in size, and it relies on a restricted version of the C standard library, which is implemented preferably by the hardware vendor. And what ends up happening additionally, and this is present in both Intel and ARM, is you have some kind of an enclave description language that kind of defines the interface of how data will flow between the trusted and untrusted parts of your project. The project would also involve some kind of complex data copying protocol. For example, in Intel, only the first layer of pointers are copied. So if you have like a nested pointer, the programmer has to manually go and copy each of these levels of pointers. So of course, this is a bad programming model, and high-level languages have been thinking about how to do this. So some of the well-known approaches are present in Go and Java, and the general approach that they take looks something like this, which is, first of all, they extend the program. They extend the language. So both in case of Go, it has a language extension which adds a separate type of coroutine. Similarly, Java has some special keywords. First of all, you modify the parser because your language has extended. And most importantly, the compilation pipeline also has to be modified such that you can track the data flow and actually work out how the data should be partitioned. Of course, this is a known undecidable problem which cannot be done automatically, so you use judicious amount of annotations, and yeah, it's not great. And of course, the runtime also needs modification. So to tackle that, our approach is through a domain-specific language, which we devise, which is called HasTEE. HasTEE is simply provided to the programmer as a library. It most importantly does not rely on any kind of compiler modifications. We do not extend the language, we do not extend the parser, but of course the runtime requires certain modifications. And additionally, we include a pragmatic version of information flow control to monitor how data moves between the trusted and the untrusted sides. So to summarize, like the key contribution is, first of all, it gives you an automatic way of partitioning your program using the type system. It does not require any compiler modifications. And you get to program in a high-level language like Haskell and not C. And you can get to enforce some kind of information flow control on the data. So let me begin by illustrating you with a simple password checker example. And I can introduce the API as well. So the API relies on 3 monads. I'm going to start with the first one. The first one is an enclave monad. So this is a fairly simple function. It gets a password string, and it maps it inside the monad and just checks that whether it maps with the password that is already present inside the enclave monad. The second one is the app monad, which is kind of like a setup monad. It sets up the applications. Then you start with this operator, which says that, okay, this is a constant that will reside inside the enclave. So you use this in enclave constant operation. It will raise the secret string into the enclave. This operation in enclave, it gives you a reference to this function. So if you see here password checker, this is referring to the password checker above. So you get like a reference to the remote function, the enclave, and you can call it from the client side as well. Then there is a client monad. What this monad does is, it's very simple. It asks the user for a password. You get the password. And this is the interesting part. It takes this enclave reference that you have, efunc, and then it gives you a way to apply the user input, which you got here. So it applies the user input. You will see the types match here. And then the gateway function mimics something like a remote procedure call, which actually calls into the enclave. And then you return the result. So this is your entire program. This program is not written as 2 projects. You will notice it is just one single program. And the way we do partitioning is by compiling it twice. So the idea that we use here is that you have your original program, which contains some parts which are secret, some parts which are untrusted. And what you do when you compile it twice is, when you compile it for the enclave side, you set some dummy data in here. And when you compile it for the client side, you put some dummy data for the secure part. So let's look at this program and how this one would be partitioned. It would look something like this. So if I again go back to the original program, you will see when I compile it for the enclave, this part of the program, the client side, this is simply substituted with a dummy implementation. Something like this you see here. And similarly, when I compile it for the client side, the enclave part will be substituted with some kind of dummy implementation, like this. In this case, the in-enclave function ignores the password checker body, and the compiler basically optimizes it away. So effectively, by doing this, what you have done is you have partitioned your program into 2 parts. And then what you can do is simply run this part of the program, which is the enclave part. You run it on the trusted runtime, whereas the untrusted part runs on the usual GHC pipeline. So if I were to show you what the tool chain looks like, so we use Cabal simply. And let's see, let me try to build this for the, enclave actually. Or let me build it for the untrusted side actually. Then we can see that let's see. -f enclave. So you can see here I'm just passing a flag. This flag is indicating that compile this for the enclave. So while this compilation runs, we can look at the code. It's exactly what you saw before. It's simply the password checker code. The only thing notable here is there is this if-defs present here. What this if-defs are telling you is that when you are compiling this for the enclave, just substitute the enclave file, and whereas on the other side, if this flag is not passed, you substitute it for the client. And if I were to look at one of these, you will find that the enclave monad has like a dummy implementation down in several parts, and something similar happens there. So okay, now this part is compiled. So if I take a look at the assembly generated here, or maybe to the binary. So let's see, object dump here. So this is the main program, and if I were to read the string parts, you will see it only stores the string secret. It's encoded in hexadecimal here. And you will see the other parts of the string, like these things, these have disappeared. And now if I do the same building, but instead of passing the -f enclave flag, if I just do it like this should ideally not contain the secret string. And we can, again, open the binary. And you can see here. So everything is hexadecimal encoded, but you can see the secret string is not present. It's just showing the strings, enter your password, your login attempted, basically this parts of the code, right? Okay, so let's return to the slides. So we have looked at how it works at the level of the binary. Now let's go a bit more at the higher level side and see what happens. So in terms of information flow control, this is a fairly simple information flow control framework, because instead of multiple labels and like a lattice, etc., we just have a low security level and a high security level. So if we were to enforce general non-interference, then you would not allow any data to flow from high to low. But we want to allow some kind of declassification to happen. And in our case, in our framework, that's done using the gateway function. So let's look at the type of the gateway function. It's fairly simple. You can see here that a secure enclave is converted into a client. And if you look at what kind of guards or protection that we have here, a very simple one that we have is that this has the binary constraint. So imagine in the enclave code, you have some kind of, like secure data, like say a private key, which you do not want to leak. So if that private key does not have a binary instance, this private key will never leak out into the client side. There's another level of security that we enforce, which is in the enclave monad, which is instead of instantiating the monad IO type class and allowing this monad to do any kind of IO effects, it instantiated a restricted IO type class where we kind of make the effects more granular, like which other effects that this can do. So those are like the two constraints that we enforce on this gateway operation. In terms of theory, we don't have a proof yet, but the general non-interference proposition for our system is this, that if you have a enclave program, a program of the type enclave A to app done, and given two enclave computations E1 and E2, if your program P does not have any gateway operations, then P of E1 and P of E2 will have the exact same side effects on the untrusted client. We have not mechanized the proof, but the paper goes into the operational semantics, and it can be used to prove these properties about our library. So now let's come back to the implementation. So the usual style in which we implement this, we have a Haskell application, you have a runtime underneath, and the runtime heavily relies on the C standard library for all kinds of operation. Specifically for Linux, we rely on the GNU libc library. The libc library gives you things like mmap, madvice, pthread APIs, math APIs, pretty much everything it relies on for that. So now if we want to host the enclave side of the application inside an Intel-SGX enclave, this glibc is absent. But instead, what we have is something called tlibc. So all of the mmap, pthread APIs, all of them become absent. So effectively, you cannot allocate memory anymore because GHC runtime heavily relies on mmap for doing memory allocation. So in that situation, how do we actually host our applications on an SGX enclave? So our framework is kind of interesting. So we have already spoken about the untrusted and the trusted application partitioning. We rely on a library operating system called Gremlin. And what this library operating system does is when it loads data onto the enclave, it takes a hash of all the libraries that it loads. So it has a manifest file where you can state that I am relying on glibc. And what it will do is it will also load glibc onto the enclave, but it does some kind of integrity checks. So if there is an operation, a call to mmap, it will make sure that the hash of glibc matches the hash when it actually loaded this onto the enclave. And another thing which it does, it narrows the system call interface sufficiently. So instead of the 200 plus system calls, Graamen gives you only like 40 system calls. And the 200 plus system calls that is missing, it's kind of implemented within the library system. But even then, the trusted runtime does not directly work with Graamen. Because again, mmap is a fairly complex function with several types of operations possible. So we had to patch mmap to remove certain options which are not supported by Graamen. Similarly, the select function call, Graamen does not have any operation for select, and the GHC-IO manager relies on select. So we had to patch that as well in our trusted runtime so that we could host this application. So this is the general framework that we have. For communication between the trusted and the untrusted part of the application, we use an IPC call, which sends and receives data between the two sides. So as you might expect, the performance is not great. So let's go to the performance. So first of all, let's look a bit at memory usage. So in memory usage numbers, this is the same password checker application, but extended a bit such that the password file is actually written on disk, encrypted, and then decrypted and read back. So the notable numbers here are that the resident memory size does not exceed 93 MB. So what is this 93 MB? The disjoint set of memory that an enclave have that is bounded by 93 megabytes. So if your memory usage exceeds that, what ends up happening is it starts swapping onto the disk. And that swaps are very expensive. Those memory get encrypted, and every time it's read back, it has to be decrypted. So at least for this particular application, this wasn't a problem, but it requires more benchmarking. As for the latency, again, in this password wallet example, we had around a 60 millisecond latency, which is much slower compared to what would happen in a native SDK, which is only around 0.6 milliseconds. Do note that the native SDK is also kind of slow because a function call in an enclave is not as simple as just making a jump. You actually have a separate enclave call instruction, which makes a domain transition into the enclave. It has to reset the registers and do a number of things. So this is one area where I think a lot of engineering can be done. For example, if we remove the library OS and actually start relying on the TLibC, which is provided by Intel-SGX, we can get to a much closer speed to the 0.6 millisecond latency in the native SDK. Finally, let's talk about applications. So we have a cool application that we built. Let me talk about one of them, which is a zero trust federated learning scenario. So in this scenario, you have two mutually distrusting parties. Firstly, a machine learning model owner. They have certain models which have certain weights which they do not want to reveal to the cloud server, which is the original threat model. But at the same time, it does not trust the client as well. If it leaks this data to the client, it's afraid that the client might use that. So the client, at the same time, it has the data, but it does not want to reveal the data to the server or the model owner because it might be confidential data like patient data or something similar. So in our scenario, what happens is that we store the ML model inside an Intel-SGX enclave. And what we do is we do the encryption of the model, and we send an encrypted model to the client. The client then trains the model on its end on the encrypted side, and then it sends the encrypted model back, and the aggregation, again, happens inside the enclave. So if you're wondering, how does the client train an encrypted model, we have a homomorphic encryption library that we have also built. So what this library does is it trains the data, and it allows you to work with very simple operations like addition and multiplication. So it is a very simple model which does linear regression, but at least it illustrates the whole example of how you can do that. And you can see there is mutual distrust across the board in this kind of application. Apart from this, we have two more examples. We have a password wallet, which is encrypted. It's kind of similar to the password checker example, which I showed you, where the password file is actually encrypted. This encryption is done using, okay, thank you. This encryption is done using a root seal key, which is a key which is found inside the enclave. And the reading of the file is also done using this root seal key. So this example can be found on the paper, and then there's a differential privacy example, which is also there. Just to conclude, I'll briefly talk about future work. A very nice generalization of this kind of compartmentalized application is available in something called Cherry. So Cherry is a project which has been going on in Cambridge for, I believe, more than the last 10 years or so. This allows very efficient sharing of data, unlike the data copying, which we are doing here. And in this case, I feel like GHC is a very good target, which can be ported to this kind of hardware. And this will give you much more efficient data sharing for confidential codes. The general threat model here is slightly different from what we have seen here. Each library, they are distrusting of each other, but we do not assume that they are all going to attack, but there might be vulnerabilities in which might sweep into the vulnerabilities of the other libraries here. So again, in this kind of work, the challenge, the obstacle lies in the runtime, because Cherry makes some very fundamental assumptions on how a pointer is represented. So we kind of need to overhaul the runtime sufficiently to make sure that Haskell can run in terms of on Cherry hardware. But as a general note, I think a lot of security critical software is migrating towards this kind of model where you have compartments. And I believe Haskell is a very good source language to experiment on ideas related to this. That is all I had for you. Thank you.
Any questions for Abhiroop?
Hello, Anil Madhavibedi from Cambridge. That was a really nice work. Essentially, at a high level, what you're doing is that you're trying to partition a single GHC runtime to run in two independent address spaces, so two different kernels. Have you considered how to just share a part of the GHC heap and just map it into both domains? And then this way, you have kind of a shared exchange heap in which values can be written and read by one, and you can avoid having the overhead of serializing over IPC. And it kind of leads on to my second question. Do your abstractions admit having multiple enclaves? So if you have, for example, 3 of them, and you're trying to run code across something, do a map across various serializations, do all the cross-compilation pieces kind of work such that you can have more than one of these things in a single application?
Thank you, Anil. I think, first of all, I'll talk about the multiple enclave setting, because we saw a very interesting related talk in ICFP, which was Haskell, which was talking about distributed programming. But I think the key idea is very similar, which is that we have 2 concrete monads, client and enclave. But if you can parameterize on that specific client, this becomes generalizable to multiple enclaves. Again, the challenge would rather lie in the runtime, like how do we modify the runtime representation? And again, the first question, which we're talking about, data sharing across 2 situations. I think in ARM in particular, ARM TrustZone, things like that, I think there's a physical separation between these things. Even the memory buses are separated. So I don't know in such case what we would do. And I also am not sure about the threat model, because the enclave's threat model is very strong. It assumes that everyone is an adversary and there is only one small portion. Whereas the compartments are slightly weaker. But so that seems like a very nice threat model to at least experiment with on this idea, the future.
Great work, thanks.
Thank you.
Hi, I'm Tadashi Saito from University of Electrical Communication in Japan. One quick question. If your work is very depends on ZLibC, so we cannot use this with like a muscle or other than ZLibC, right?
Not really, because that's basically, so muscle allows, so we have actually played with muscle as well, because initially the model inside the enclave is you want to statically link everything and go up. And I don't think glibc supports full static linking. So we kind of tried to do that, but that did not work. But absolutely the framework. So in the manifest of this Gremlin library OS, instead of pointing to the glibc, if you point to muscle, it is going to link those. The point is that it requires, so GHC heavily relies on mmap. So it's a problem with GHC that mmap is, and tlibc only gives you malloc. So yeah, it kind of boils down to that.
Yeah, but mmap is included in POSIX, so it's kind of portable function, right?
So not in TLibC that I'm aware of, but if TLibC, which is Intel's libc, if they provide support for mmap, and I suspect they're working on it right now, so yeah, then it would be very simple to do that. And we wouldn't need to go through this library OS route as well.
Okay, thank you.
Yep.
All right. So no questions online. So let's thank.
I think Ben has
Sorry, Ben. No, go ahead. We have the time. I haven't saw it.
Ben Gamari, well typed. It seems to me like bringing in the entirety of the GHC runtime system is that significantly blows up your trusted code base,
That's
especially
true.
given you need a whole operating system then to support it.
Yeah.
So have you thought at all about how plausible it would be to instead get rid of most of the dependence of just the enclave bit of the mutator, right, that you actually want to run. And this would also probably allow, in process, avoiding having this process barrier, which would improve performance as well. And it would be, I think, not maybe that hard, right? You just need a nursery in the enclave, and then you need to bound the amount of allocation you can do, but that's probably doable for most applications. Have you considered this at all, or is this?
So again, I'm not sure in situations like TrustZone how that would be supported, where the physical placement of these things. So I believe like in all of these cases, like say the nursery, and say you have the nursery here and the older generation here, they live within the same virtual memory space, right? But in case of things like ARM TrustZone, they are physically separated.
I mean, you could arrange for them. Not
You could
to be,
arrange
but
for
yeah,
them,
I
of course,
guess
and I don't know the cost for that, but
yeah.
positively, this is something which we are trying to look at, and I really wanted to talk to the JHC team about this, like how would I get rid of the library operating system? It was just because we are prototyping, this
Yeah,
is
of
like
course.
a fast path to prototype,
No, it seems
but
like nice.
that will positively, like, reduce the trusted code base and improve the performance.
Great,
So,
yeah, thanks.
Yeah.
Any more questions for Abhiroop? All right. Then thanks, Abhiroop, again.